Chemical rockets are the best way we have to get people off planets right now. One of the things that makes chemical rockets so useful is that they create both energy and propellant through combustion. But they have almost reached the limit of their efficiency. To go beyond what they are capable of, we will need to develop new methods of propulsion. At the most fundamental level, all rockets are throwing mass out the back so they can go forward. When we heat a solid, it becomes a liquid. When we heat a liquid, it becomes a gas. When we heat a gas to a high enough temperature, it becomes a plasma. A plasma is a gas where the electrons have been knocked off the gas particles. The resultant ion and electron move freely around each other. Ionization can occur by heating the gas to an extremely high temperature or hitting the outer electron with a photon of the correct wavelength to allow absorption, where the electron absorbs the energy of the photon and can leave the gas particle. Now the remaining gas particle is an ion. Ions can be manipulated by magnetic fields. We can use a magnetic force field to keep the gas particles from touching the walls of the rocket engine. Then there is no transfer of kinetic energy. The resultant plasma can be hotter than the core of the sun, and the engine won't melt. There will be some photon emission from the plasma, which will heat the engine some, but this can be controlled with the same type of active cooling we used on the chemical rocket engines. We can then open a gap in the magnetic field, which acts like a throat in a chemical rocket engine, allowing the heated ions to flow out of the engine. This is how the Variable Specific Impulse Magnetohydrodynamic Rocket, or VASIMR, works. We call this type of engine electrothermal, since we are using electromagnetic forces to heat the propellant, then letting thermal energy expel it out the back. There is another way also. We can keep the ionized gas relatively cold, then throw it out the back with electromagnetic energy. These were called particle accelerators when they were invented in the 1920s, and when we take them to space and use them for propulsion, they are called ion engines or ion drives. We made an in-depth survey of ion engine technology in this lesson. Now let's do an update on the latest advances for one type of ion engine. This is called the Magnetoplasmadynamic thruster. In this type of thruster, a gas is first ionized. This means an electron is knocked off to create a charged particle. These ionized particles are then sent into a chamber called the acceleration chamber, where they are exposed to powerful electric and magnetic fields. If you use electric fields to eject ions, you have an ion thruster. If you use magnetic fields to eject a plasma, you have a magnetoplasmadynamic thruster. Now let's look at another relationship between electricity and magnetism. If you run a current in this direction, you will create an electric field in this direction, and also create a magnetic field in this direction. We can use the right hand again and show it this way. Current in the direction of the thumb, magnetic field points toward the fingers, electric field rises out of the palm. This magnetic field is called the Lorentz force, after Hendrik Lorentz, who derived it in 1895. The Lorentz force is a force felt by a particle when it travels through an electric or magnetic field. The particle of charge Q, moving with a certain velocity, represented as V, will feel a force in accordance with the equation F equals QE plus QV times B, where E is the electric field and B is the magnetic field. This equation shows that the electromagnetic force felt by a charged particle is a combination of the force generated by the magnitude of the electric field E, measured in volts per meter, times the charge on the particle, which we measure in coulombs, added to the velocity of the charge, times the charge of the particle, multiplied by the force generated by the magnetic field B, measured in Teslas. In other words, the electromagnetic force felt by a charged particle is a function of its charge and velocity. I don't pretend to understand why things are this way. That's for electrical engineers and physicists. But to understand ion engines, we need to understand that it is this way. This is how a magnetoplasmadynamic thruster works, and these are sometimes called Lorentz accelerators. We are using magnetic fields to make plasma move. Let's look at this design. Here we see a central post with a circular wall out here. If we run an electric current, a charged particle thrown into this chamber would feel a Lorentz force throwing it out of the engine. These are also called Lorentz force accelerators. In Japan, they are also called MPD arc jets. Magnetoplasmadynamic thrusters come in two types. The first is where they depend only on the generated magnetic field. This is called a self or direct field MPD. And when they augment this field with an external magnetic field, it is called an applied field MPD. These thrusters can use any propellant that can be converted to plasma. This would include the noble gases like xenon, argon, and neon, as well as hydrogen and hydrazine. The best performance, however, is generally with lithium vapor. Remember that lithium is the lightest metal available to us. MPD thrusters have the potential to produce extremely high specific impulse. up to 11,000 seconds theoretically. 3 times better than xenon-based ion drives, and 25 times better than the best chemical rockets. But whereas most ion drives have an extremely low thrust, MPD thrusters have the potential to achieve a thrust of up to 200 newtons. This may not sound like much, but the thrust of most ion drives is measured in micro or millinewtons. The most powerful ion thruster to date, NASA's X-3 Xenon Hall thruster, has a mass of about 230 kilograms and can only produce about 5.4 newtons. Magnetoplasmadynamic thrusters were developed in the 1960s, first in Germany, then researched in both the United States and the Soviet Union, with Japan and other countries coming on board later. Japan flew the first MPD in space in 1995. Let's review the basic design. An MPD thruster has 2 metal electrodes. In the center we see a rod-shaped cathode, surrounded by a cylinder-shaped anode. There is an insulator in between. A high current is created between these. The cathode heats up and high-speed electrons are emitted, and electricity arcs across. A gas is then put in this chamber, where it is struck by the high-speed electrons and ionized. Current, when described as flowing from positive to negative, is able to flow from the anode ring to the cathode rod through this ionized gas or plasma. Plasma can conduct electricity. A magnetic field is created around the cathode as electricity goes through it, like any wire would, and this is called the self-field. The self-induced magnetic field interacts with the electric current flowing from the anode to the cathode through the plasma. This creates a Lorentz force that throws the plasma out of the engine at very high velocities, producing thrust. So far, this is a direct or self-field MPD. To boost thrust, you can apply an external magnetic field to augment the one produced by the current flowing through the cathode rod. This is an applied MPD, and it is much more efficient. The problem has been that to get this to produce a lot of efficient thrust required a very heavy energy-intensive magnet. These were developed first in Russia and have produced over 100 kilowatts of power, with an efficiency of up to 45% and an ejection velocity of 15,000 meters per second, which of course means a specific impulse of 5,000 seconds. Lithium and hydrogen-based systems have been developed by NASA at the Jet Propulsion Laboratory and the Glenn Research Center. Japan flew one of these in 1995. Why doesn't everyone use these thrusters? They are energy intensive. They do not produce their own power like a chemical rocket. This means you will need a power source. Solar panels are an option, but are limited to about 40% efficiency with current technology, with the solar flux at the orbit of the Earth being a little less than 1,400 watts per square meter. We are looking at about 560 watts of power. A 10 meter by 10 meter solar array is quite large, and would give us only 56 kilowatts of power when exposed to sunlight. We would need 2 of these just to power one 100 kilowatt MPD thruster. Nuclear reactors producing several hundred kilowatts were flown in space by the Soviets in the 1980s. And Rolls-Royce of the United Kingdom is working on one now, as is the United States and China. Fusion reactors may be available within a decade, but let's assume not and go fission nuclear. What could we do with a 3 megawatt reactor using MPD technology? One of the most energy-intensive components of an applied field MPD is this. This is the external magnet. To make the thruster efficient and powerful, you must apply an extremely strong external magnetic field. How can we solve this problem? To create a strong field, you must have a powerful current. Running a lot of current through metal generates heat, which robs some of the power, and reduces the power available to produce the magnetic field. This has been a problem with electromagnets since they were created. If you watch this lesson on the spark reactor, you will see that an advanced fusion reactor designed by physicists from MIT uses an advanced type of superconductor tape. There are 4 lessons focused on superconductor technology and its application to spaceflight. I highly recommend reviewing these. One of the things we covered in those lessons were superconductors. Superconductors have no resistance to the flow of electricity. This allows more of your power to go to propulsion and increases the efficiency of the system. This is an MPD thruster with only a direct field. It is okay, but not much better than other devices. This is an MPD thruster with an applied magnetic field. The field is being generated by a regular electromagnet. The thruster might only have a mass of 13 kilograms by itself. By itself, this is a direct field MPD. If we add this magnet, we greatly increase the efficiency of this thruster. But while the thruster itself might only have a mass of 13 kilograms, the magnet has a mass of 150 kilograms and absorbs 285 kilowatts of power. If we create an applied magnetic field of 100 millitesla with a current of 750 amps using 100 volts, we can process 90 milligrams of propellant per second, producing 2.1 newtons at a specific impulse of 2,400 seconds. and an efficiency of 33% of the power applied being converted into thrust. We can do this using 75 kilowatts of power. If we increase the power of the magnetic field to 400 millitesla, which can be done by increasing our power just 33% to 100 kilowatts, we can drop the current by 41% to 440 amps, and increase the voltage by 130% to 230 volts. Remember, it's the amps or current that damages your equipment. Running at a higher voltage and lower amps makes the system last much longer. Older MPD drives had problems with the cathode rod eroding away, but this problem has been just about solved with newer technology, using lithium vapor propellant and by lowering the amps. The same engine, with a more powerful magnetic field, can process less propellant, only 60 milligrams per second versus 90 milligrams per second before, a savings of 33%, and still produce a thrust of 2.75 newtons, a gain of 31%, with a specific impulse of 4,665 seconds, almost double, and with a 62% efficiency power conversion to thrust efficiency. This shows that you can get the same or even a little more thrust from the same engine, processing less propellant, at a much higher efficiency. This allows you to carry a lot less propellant, or move a lot more mass. What is the next step in these engines? What if we use a superconducting magnet instead of the heavy regular copper electromagnet? To produce superconducting magnets, some companies are looking at using Rebco. Rebco is a rare earth barium copper oxide tape to make superconducting magnets. These magnets are able to superconduct at about 77 Kelvin, the temperature of liquid nitrogen. These are called high-temperature superconductors, even though they still operate at very cold temperatures. Using a superconducting tape magnet would be extremely useful in this concept. This is the supreme Magnetoplasmadynamic thruster. No, I'm not being dramatic, that's the name of it. It stands for Superconductor-Based, Readiness-Enhanced, Magnetoplasmadynamic Electric Propulsion. This is made by a company called Neutron Star Systems out of Germany. This is a very innovative company that is applying superconducting technology to several areas of spaceflight. Superconducting Rebco tape has become affordable over the last few years. There are several companies producing it in Europe, the United States, and elsewhere. If we apply this magnet technology to MPD thrusters, as Neutron Star Systems plans to do here, we should be able to dramatically improve the performance of these thrusters. Here you see a propellant supply and a power processing unit. These feed into the discharge unit, where the propellant is ionized into plasma. And here you see a superconducting coil being placed around the thruster to accelerate the plasma. They then add a thermal management system, which would be insulation and cooling systems, to keep the magnet below its critical temperature. Using a superconducting magnet instead of a regular electromagnet can reduce the mass by a factor of 4, while reducing power consumption by a factor of 300, and still produce a field 4 times stronger. Let's dwell on that for a moment. If the greatest limitation to the use of this advanced propulsion system is the power consumption, and you use superconducting magnets to reduce power consumption by a factor of 300, you go from needing 3 megawatts to needing only 10 kilowatts. Power to waste. Current systems are around 1,500 seconds, but up to 11,000 seconds is theoretically possible. With up to 200 newtons of force per thruster, this is all within our reach. For our propellant, we could carry tanks of argon up with us. This would be inexpensive and quite effective. It takes about 3,200 meters per second of delta V to go from low Earth orbit to a translunar trajectory orbit. Since we aren't going to go into orbit around the moon or land, we'll just get close to the moon and come back to Earth. We use the rocket equation to see how much propellant we will need to bring with us. We have the specific impulse and delta V needed. And remember, our ship had a mass of only 2,000 kilograms. We need to produce a delta V of about 3,200 meters per second, and we know that the specific impulse is 5,000 seconds. We can now try to find our final mass. So we rearrange our equation. Delta V equals the exhaust velocity times the natural log of initial mass over final mass. Delta V over exhaust velocity equals the natural log of initial mass over final mass. E is a constant, 2.7183, and we need it to get the inverse of log. E to the power of delta V over exhaust velocity equals initial mass over final mass. And now we move our final mass over and up here, while moving these over and down here. Now, final mass equals initial mass divided by E to the power of delta V over exhaust velocity. Now we will turn our specific impulse into exhaust velocity using this equation. VE equals specific impulse times the force of gravity on Earth. We get our answer by multiplying our 5,000 seconds of specific impulse by 9.807 meters per second squared, the force of gravity on Earth. This gives us 49,035 meters per second for our exhaust velocity. So we will set our initial mass as 2,000 kilograms and plug in our numbers. Our final mass comes out as 1,874 kilograms. With that, we can calculate how much propellant we will need to take with us. 126 kilograms. That's the amazing potential of ion drives. We only need 126 kilograms of propellant to get the job done. To be safe, we'll bring one a little bigger, holding about 200 kilograms of propellant. Liquid argon has a density of 1,150 kilograms per cubic meter. For 200 kilograms of liquid argon, we will only need a volume of about 0.174 cubic meters. That means a sphere 28 centimeters across, about 11 inches, can hold our propellant. We would only need one carbon overwrap pressure vessel about this size. Now we also need to worry about thrust. Propulsion efficiency tells you how much of your mass will need to be propellant to get to your destination, but thrust determines how long it will take you. Most ion propulsion systems have very low thrust. That means they have a very low acceleration. When a solar storm heated and expanded the Earth's atmosphere recently, the increased atmospheric density was a threat to SpaceX Starlink satellites, as they tried to climb slowly to their higher orbits. Sadly, the atmospheric drag increased by 50%, and this was too much for the krypton ion drives. The Starlink satellites could not stay in orbit and burned up in the atmosphere. We said earlier that magnetoplasmadynamic thrusters can produce up to 200 newtons of thrust. Let's have 10 of these thrusters putting out a total of 2,000 newtons. How fast would we go through our propellant? Another equation tells us that force equals exhaust velocity times mass propellant flow. In this case, the force is our thrust. Mass propellant flow is usually given as m dot. The dot system was developed by Isaac Newton when he reinvented calculus. This notation is called Fluxion notation or dot notation. Another mathematician named Leibniz figured out calculus a long time after Newton, but published it about the same time, as Newton had procrastinated. Leibniz notations look like this. This is the same differential equation, now clearly saying the change in mass over the change in time. It's interesting to note that the two gentlemen disagreed about who was first, and the matter was settled by an organization headed by Sir Isaac Newton, who decided that he had, after all, been first. By the way, Babylonian clay tablets show that their astronomers, over 2,000 years ago, had developed a type of calculus to track the motions of the planets and stars. And we now know that the ancient Greek scholars Eudoxus and Archimedes had developed differential equations of their own, hundreds of years before the Babylonians. Imagine where we would be today if this knowledge had been better preserved. I like Leibniz notation better, but it is traditional to use m dot in aerospace science. By the way, Newton used the notation v dot to indicate acceleration. So if you see that somewhere, it stands for the change in velocity over the change in time. Now we can rearrange the equation to solve for mass propellant flow, and we get m dot equals F over VE. In this case, 2,000 newtons divided by 49,035 meters per second equals 0.041 kilograms per second. If we need to process 126 kilograms, that means it will take 3,098 seconds. So we can calculate that it will take about 52 minutes to process our propellant through the engines. The Apollo missions, using the Saturn IVB third stage, had more thrust, but much less efficiency, less than 10% the efficiency of what we have. The S4B third stage had a fueled or wet mass of 119,000 kilograms and a dry mass of 10,000 kilograms, with a specific impulse of 421 seconds. They needed about 90% of the third stage to be propellant, but their more powerful J2 engine did produce over 1 million newtons of thrust, allowing Apollo 8 to do their injection burn in only 318 seconds, which is about 5 minutes, creating an injection velocity of 10.82 kilometers per second. If we had 7.8 kilometers per second in low Earth orbit and added 3.2 kilometers per second of delta V, we'll have 11 kilometers per second to raise our apogee out to the moon. So we ignite our ion drives, generating the needed delta V, and fly to the moon. We've packed some sandwiches because it will take a while. It took Apollo 8 68 hours to get to the moon, and they had to make some tiny course corrections. We might also. Though they went into orbit around the moon, we are going to cross in front, as you see here. We just need to make sure our flight computer is accurate, and that we chose a good date and time for our launch, so that the moon will be where we need it to be when we get there. And we had to light our engines at the right place in Earth orbit, which would be the opposite side of the Earth from where the moon's going to be. It also turns out the Earth's gravity well is much steeper than the moon's. We climb slowly up until their respective gravity fields are equal. Apollo 8 was 377,349 kilometers from the Earth at their greatest distance. And this equal gravity point was just 62,377 kilometers from the moon. The moon's gravity is 1/6 that of Earth, and the halfway point for gravity is about 1/6 the distance from the moon to the Earth. This is where we will find a spot called L1, or Earth-Moon Lagrange Point 1. Since the Earth-Moon gravity is balanced here, we could hang out without using much propellant to stay in place, relative to the Earth and Moon. We had several options when we chose our flight path. Apollo 8 fired a lunar orbit insertion burn, so they could stay around the moon. We won't, since we need to get back home before anyone gets worried. Every orbit must have two foci. We could have chosen the Earth and the Moon, like Apollo 8. They crossed in front of the moon in its orbit. This allows the moon's gravity to pull them back and slow them down, helping them to get into orbit around the moon. They did a lunar orbit insertion burn and orbited the moon a few times, traveling around the far side of the moon. We have chosen something different. We have chosen to use L1 as the other foci of our orbit. This way we never lose sight of our home planet. It is possible to use the hills and valleys created in space-time by gravity in this way. We are not moving fast enough to crest the hill and fall toward the moon. We travel around this curve, shown in a diagram where they make the gravitational landscape two-dimensional. Here we reach the apogee of our orbit and get a close-up look at the moon. We don't really have to do anything at this point. We will slowly start to fall back toward the Earth. Having planned our trajectory correctly, we'll now head back home. Now we find ourselves coasting down this slope to the Earth. This is a long hill, and we start building up a lot of speed. We will, in fact, impact the Earth's atmosphere at over 11 kilometers per second. One of the most difficult things about spaceflight is re-entry. The Apollo capsules had these thick heat shields. We don't have one of those. We might think about firing our engines to come to a stop before we hit the atmosphere, but even with an efficiency of 5,000 seconds specific impulse and a mass of 1,874 kilograms, we would need 377 kilograms of propellant to stop our fall, and as soon as we came to rest, we would start falling again. But we started with only 200 kilograms of propellant, and we've already used 126. We have only 74 kilograms of propellant left. With a mass of 1,874 kilograms after burning our propellant to get here, and moving at 11,000 meters per second, we have a momentum of over 20 million kilogram meters per second. If we hit the atmosphere at this speed and momentum, we will generate a shock wave with a temperature of over 20,000 Kelvin. Now there will be a boundary layer of stagnant air between our ship and the atmosphere. This will prevent conduction and convection, but it does allow radiative heating. The photons generated by the shock wave will create a temperature of about 1,650 Kelvin against our ship, which is 1,377 Celsius or 2,511 Fahrenheit. Carbon fiber and even titanium cannot tolerate these temperatures. Things are going to get really bad really fast if we can't think of something. But remembering our classes at the Terran Space Academy, we came prepared. We knew that Neutron Star Systems out of Germany doesn't just make our magnetoplasmadynamic thrusters. They also make something called MEEST. MEEST stands for Magnetohydrodynamic Enhanced Entry System for Space Transportation. The European Union has invested 3.5 million euros into this research. This system uses a powerful superconducting magnet to generate a large rotating magnetic field around the ship. Ions are then released into the field to create a physical shell that will interact with the atmosphere and create resistance, greatly increasing the effective surface area and therefore reducing the mass to surface area ratio. Reducing this ratio increases the braking rate and reduces terminal velocity. We'll still have to make sure to come in at the right angle. If you brake too fast, you could generate too many G-forces and injure yourself. But if we brake too slowly, we'll have a longer heat pulse, increasing our heat load and causing a problem in most ships. The re-entry angle of the Apollo capsules was about 6 degrees. But our magnetic ion force field will hold the shock wave further back from the ship. Since radiative energy reduces by the distance squared, we can keep the shock wave away from the ship and prevent too much heat transfer. We have the superconducting magnets and our applied field magnetoplasmadynamic thrusters ready. We feed most of our power to the Magnetoshell, saving some to generate ions, creating our Magnetoshell. The magnetic field created grabs the plasma and holds it around the ship. The sphere extends out far from the ship. Magnetoshells of up to 100 meters in diameter are believed to be possible. This shell of ions actually impacts the Earth's atmosphere, where the ship's kinetic energy causes the atmosphere to heat, and then becomes plasma. But the plasma from the atmosphere is conductive, like all plasma is. The magnetic field grabs this plasma and adds it to our shield, reinforcing it. And as the distance from our ship to the shock wave is now much further away, the radiated heat is much less. No problem for our ship. Once the ship slows from the friction of this giant plasma sphere, the shock wave dissipates. Without the shock wave generating plasma, our sphere starts to fade away, as magnetic fields cannot move neutral air particles, and we are almost out of propellant. So we angle our ship down a little and feed air through our atmospheric ion engine scoops, not for propulsion, but to maintain our plasma shield. The ship continues to slow until reaching terminal velocity, which, with such a large surface area, is only about 150 kilometers per hour. At this speed, we can turn off our Magnetoshell and just use our engines with ducted fans to slow our descent and land gently in our driveway.